Some announcements before we start. You finished your last Peruse All assignment. So if you didn't do it before class, well, at least you're here with your headphones in. If you didn't do it before class, well, you didn't do the last one. The
this morning?
Peruse All is always due before class time.
Sorry.
The last homework assignment is due this afternoon or this evening, tonight, whatever time you do it. The last lab assignment is due tomorrow at midnight, and the last scrapbook submission with 5 additional entries covering anywhere from chapters 1 to 17 is due Friday before sundown. Make sure for your final submission, you won't be marked off if you only have your 5 final entries, but you won't get extra credit on your scrapbook if you only have the 5 final, because I want to look at the entire scrapbook as a whole in evaluating which ones get the bonus points for compelling scrapbook.
So what's the criteria?
Well, the criteria is very fuzzy. It's which ones I think are the most outstanding. And so, things like it's easy to find, the sections for, the relevance and that kind of thing. And it's visually appealing and the index is easy to follow to find the topics. Those are the kinds of things I'm using for judges.
Index?
Yeah.
Oh. So we can change it before we turn it into?
Yeah.
So you're supposed to have an index with each thing? Where?
Yeah, it would be after the cover page and before the first entry.
Like an index of each thing that you went over?
Yeah, like I have in the sample that I gave you.
Okay. What about that?
I mean, that only comes into evaluation for the evaluation of the entire scrapbook for extra credit.
Okay.
Right. The regular credit is just based on the entries. Okay, final thing. For problem 5 on the homework, it says assume that the speed of sound in helium changes in the same fashion as it changes in air. You have to use that form for the speed of sound. Remember in the lab book you had 2 forms for calculating the speed of sound in air, and one of them was 331.5 plus 0.607 times temperature C. That's a linearization of this equation where the number out front is 331.5. If the number out front is 965, you can linearize it in the same fashion, but it's not going to be the 0.607. So just use this form of the equation and you won't have a problem. So just wanted to make sure that that's known. Otherwise, use the other one. You're like, what? I assumed it followed the same and got a completely different answer. So nothing new today. So technically, I'm giving you 2 dead days instead of 1. The last day of every class is technically a dead day. And in that dead day, not supposed to have major assignments. You actually can have new material, but no new material. Let's just review. Chapters 1 through 17 will be covered on the exam. As I was writing the exam, I was like, but I only have 10 knowledge questions and I have 17 chapters. I'm actually going to give you 16 knowledge questions, 1 for chapters 1 and 2, and then 1 for each chapter thereafter. So there will be more in the knowledge section than there were on the other tests. Otherwise, it will be the same. You'll have basically 1 question from each test section for the application, and then there'll be 1 additional, beyond that to get to 6, so you can drop 1. And it will be, 1 test section will be skipped in the synthesis because I'm only going to have 4 there, and technically this is the last test section and it's the 5th one. Just make sure you understand the layout. Any questions about how the layout's going to be on the test? Andy?
So it's 16 knowledge, 5 application, 4 synthesis.
It's going to have 16 knowledge, 6 application, 5 of which you do, 4 synthesis, 3 of which you do.
Okay. And then the 6th application, it's one from each section that we tested on.
The
Like sectioned out the same way that the tests were sectioned out.
yes, except for one extra, because there's only 5 tests and there would be a 6th. But yeah, that's so one test will have 2 from it, all the rest will have 1.
Okay. Thank you.
And I'll probably put 2 from the section after the last test we had, so you have to do at least 1 question on the material after the last test. That's the only way I can assure that you have to do it, right? Any other questions about the final exam layout? All right, then let's get in. So, chapter 1, going way back. Now, chapter 1 probably wasn't startling or shocking or difficult to most of you, but like when you get to chapter 2, 3, I know those things were hard when they were first introduced, and now they'll probably seem easy. If they seem easy, good, we've learned. That's why we give cumulative finals, because we want to make sure you learn through the semester, not just put something in your head and extracted it later. So in chapter 1, we talked about what science is about. And so we have things that we've been using throughout the semester, things like you need to know how to do scientific notation. I could ask you a question about scientific notation, significant figures, the base units and derived units, kilogram, meter, second, those are base. Newtons, derived, joules, derived units. Prefixes, kilo, centi, you need to be able to use those. You shouldn't raise your hand and say, now, what is a megameter again? You should know mega means 10 to the 6th. Dimensional analysis, that's just making sure your units are right. And graphing things like, I've done a lot of graphing. So that's not a lot to be worried about there. One thing that I didn't list there that I really should have had here is the scientific method. We have had the scientific method over and over in lab because all of science is science because it's built in the scientific method. That is the way we learn stuff, is by making a hypothesis, testing that hypothesis, and so on. So make sure you do know the scientific method as well. Chapter 1 or 2, we got into kinematics. Kinematics, how things move. So we had to know our kinematic variables, things like what's the difference in speed versus velocity. Max, what's the difference in speed versus velocity?
Speed has no direction. Velocity has direction.
Right. Speed has no direction, velocity has direction. Otherwise, they're telling you how fast something's going, their change in position over time, acceleration, right? These, at this point, this is all, it should be really basic to you, right? Everybody with me so far? And this is basic to you now, even though it wasn't when it was first introduced necessarily. Then we have the kinematic equations. Kinematic equations, you don't have to have them memorized, of course, but you have to know which one to use in which situation. So for instance, in homework problem 1, for the assignment today, you drop a rock, it hits the water, you hear the sound sometime later after you drop the rock. When the rock is dropping, which kinematic equation you're going to use to relate the distance and the time? How do you make that decision?
You look at your known variables and choose which one based on that.
Yeah, you look at your variables and choose the one based on that. If you don't know a variable and you don't care about the variable, look for the equation that doesn't have that variable. And so in that case, you use the one that we use 90% of the time. Distance is equal to initial position plus v initial t plus 1/2 at squared. And you get an equation for the distance it drops as a function of the time it takes to drop. And then for the sound coming back up, which kinematic equation you use. It's not an object now, it's a sound wave, but it's still doing the same thing. It's traveling with a constant velocity, which means you know the acceleration is 0. You use the same equation. Distance is equal to, initial position plus speed times time plus the acceleration, which is 0 times time squared, divided by 2. I've got that. So make sure you're comfortable in choosing which equation to use. And then problem solving steps. If you're solving a kinematics problem, And back when we learned this, we only had one type of problem. I gave you steps. Remember in lab, I gave you steps of how to, the lab where we didn't do lab, but we did problems. Steps on how to approach each different type of problem. That's something that you really want to review. Because you're going to have to solve problems of different types, and now it's going to be more difficult than it ever was because you have more types of problems. So the first step is to identify what type of problem it is. Here it's a kinematic problem. If it's a kinematic problem, well, you need to draw your situation and then determine your knowns and unknowns. Determine which kinematic equation to use, and then solve it. And then make sure your answer makes sense. Chapter 3, we introduced two-dimensional motion. Two-dimensional motion, we had to do things that, some things might still be a little confusing. Things like resolving a vector into components. If I have my component directions, how do you choose component directions? What's your highest priority rule for choosing component directions?
Tail and head, isn't it?
No, that's for vector addition. For just choosing the direction of your x and y coordinate system.
One of them, usually x, goes in the direction of acceleration.
Okay, your first priority is choose directions. So if there's an acceleration, one coordinate direction is parallel to that acceleration. Why? Because then when you apply Newton's second law, which we get to in chapter 4, your acceleration, your sum of your forces in one direction is 0 because the acceleration in that direction is 0. I couldn't hear what you said, Judith. You might have said exactly the same thing. I just couldn't hear.
I couldn't get the words out.
Okay. So your first priority is make sure that you have your coordinate system set. So if there's an acceleration, it's in one direction, one of your coordinate directions. Otherwise, you want, well, all of it is, we want to make things as simple as possible. So the next simple thing would be if you have no acceleration, choose the direction that's going to have most of your vectors already resolved into components. That is, if I have two vectors that are 9 degrees from each other, I'll choose a tilted coordinate system so that those are both in coordinate directions. And then, of course, a third priority, like the standard, we usually use horizontal and vertical. But then if you think about it, why do we usually use horizontal and vertical? Because usually our acceleration is vertical. That's why that's the standard. Okay, so independence of motion means once you have identified your coordinate directions, the motion in the x direction is completely independent of the motion in the y direction. And so a real life problem with two-dimensional motion, such as tennis ball sitting on my desk, not going to throw this to anyone. But when you throw a ball, you have the vertical motion, acceleration is in the vertical direction. You have the horizontal motion, and you solve both problems separately, and then time is what ties them together. So make sure you're comfortable with that. Solving a two-dimensional problem. I do have here vector addition. Make sure that you can add vectors graphically. Analytical, make sure you can break vectors into components mathematically using trig functions. So make sure that you remember how to determine if you're going to use sine or cosine for each component. Unit vectors, just a reminder, unit vectors have a magnitude of 1. That's what unit means. So they have a magnitude of 1, and they're just telling you the direction of the vector. And, well, projectile motion, that's looking at something like this. Chapters 4 and 5 are dynamics. Dynamics, kinematics was talking about how something moves. Dynamics is talking about why it does that. And so dynamics is where we introduced forces. What's the definition of a force? Anything that
Acts on another object.
acts how? Anything that pushes or pulls. Acts is a fair word. For instance, we usually say for Newton's third law, for every action, there's an equal and opposite reaction. Acting, action, same thing. And action and reaction meant forces. So this is where we had Newton's 3 laws of motion. That an object will stay in constant motion unless a net force acts on it. That the net force on an object is equal to the mass of that object times the acceleration of that object. And the last one, for every action is equal opposite reaction. Make sure that you're comfortable with those 3 laws, and of course, especially solving problems. The second law is the one that we use by far the most. Sum of the force vectors is equal to mass times acceleration vector. When you're using the Newton's second law problem, you need to identify the object you're working with. And then the m is the mass of the object you're working with. You draw a free body diagram. What is a free body diagram? It's a diagram showing all the forces acting on your object. Not all the forces that exist, only the ones that are acting on the object. So as a reminder, right now, I'm standing on the ground. What forces are acting on me right now?
Gravity
Okay, normal force and gravity. What direction is the normal force pointing?
down, no, up from
Up.
the floor.
Because the normal force is what's keeping me from falling through the floor. By definition, it always acts out of the surface. So, just to make sure we're clear on normal force, because it's been a while, when I push on the wall here, what direction is the normal force pointing on me? Out, right, out of the surface. And then we have the force of gravity acting on me down. What about the force of my shoes pushing on the floor? Does it exist? It exists, but it doesn't go on a free body diagram because it's not acting on me. It's acting on the floor. It's me acting on the floor. The one that goes in the free body diagram is the floor acting on me, which is normal. So the force of my feet pushing on the ground is the third law reaction force, the equal opposite force to the normal force acting on me. Now I have here a list of forces, force of gravity. We had 2 forms of the force of gravity. Force of gravity is equal to mg. That's an approximation for if you're on the surface of the earth. Then we had force of gravity is capital G times mass of object 1 times mass of object 2 divided by r squared, where r is the separation between the centers of the 2 objects. That's the universal law of gravitation. That works for anything. What direction is gravitational force between any 2 objects?
Away from each other, right?
You're doing good at reversing everything.
Towards each other.
Always towards. Gravitational is an attractive force. Everything is attracted to everything else gravitationally. So we're attracted downward to the center of the earth. We feel that force very strongly. But we're also attracted to everyone in this room. We don't feel that force. Why don't we feel that force? Because it's so small. Now the distances between us are much smaller than the distance between us and the center of the earth. But the mass of the earth is enormous compared to the mass of a person, clearly. And so when you take the mass of the earth divided by the separation between us and the center of the earth squared, that's actually a much bigger number than the mass of your friend divided by the separation between you and your friend squared. Tension force, that's a force that's going through a string or a chain or something. And then finally, spring. We've just been talking about the spring forces, right? When we talked about simple harmonic motion. So that was a good review for how spring forces work. By the way, you notice the cross-outs. Those are things that are in those chapters we didn't cover. Uniform circular motion and gravitation. This is actually where the law of universal gravitation was introduced. I introduced it before because we had gravity there. This is where we start talking about rotational motion and talking about angular velocity. We've just been talking about angular frequency. Angular velocity and angular frequency are fundamentally the same thing, just used in different contexts. So remember your units for angles, radians versus degrees. Make sure you flip your calculator as necessary. so you don't make a mistake with your calculator being in the wrong units. Sign conventions. What direction for an angle is considered positive?
Clockwise?
Oh, hey, look, David chose the right direction this time. Counterclockwise. It comes from the right-hand rule. If you wrap the fingers of your right hand counterclockwise, your thumb points out, and we consider that positive. If you wrap them clockwise, your thumb points away from you, we consider that negative. So angular velocity is something is rotating in a clockwise direction. That's a negative angular velocity. Counterclockwise is positive. Angular acceleration, likewise. Angular acceleration is an increase in the rate of rotation, whereas linear acceleration was an increase in the rate of motion. Rotational kinematic equations. They're identical to the linear kinematic equations, except for the variables are changed from the linear ones to the angular ones. So if you could do the linear kinematics, you can do rotational kinematics because it takes the same knowledge. Centripetal acceleration is a good one. Centripetal acceleration, number one, it never shows up on a free body diagram. Why doesn't centripetal acceleration show up on a free body diagram?
Isn't it because it's a fictional force?
Centrifugal is fictitious. Centripetal is real.
Because it's based on the moment of inertia. No, it's still small.
It's what? It's a resultant. It's the result you get when you add up all the forces in your free body diagram that are in the direction toward the center of rotation. So it's not a force acting on an object. It's the sum of the forces in the direction toward the center when something's going in a circular path. So it's because it's a resultant. It's not an actual force acting. It's the result of all the forces. And so the centripetal acceleration is the acceleration toward the center necessary to stay in a circle. That's A sub c is equal to v squared over r. I know, capital R, lowercase r. I just chose capital today. And the centripetal force is equal to the sum of the forces in the center direction. I know I use c both places here. Is equal to mass times the centripetal acceleration. And so the definition of the centripetal force is mass times the acceleration toward the center, and it's whatever causes them. So as my last words on centripetal force, if I swing this about in a horizontal circle, what is supplying the centripetal force?
Isn't the acceleration in the tangential direction?
Well, what is causing, what force is actually acting toward the center?
The strength.
The tension and the strain. Now, the tension and strain also has a vertical component. If it didn't, of course, the bob would fall. And so the centripetal acceleration is the horizontal component of the tension, and then you have the vertical component of the tension has to be equal and opposite to the force of gravity, or it accelerates upward or downward. Here's a good question that's not on the final exam, but the ideas are good to review. If I swing this around, why doesn't it just fall like that when it gets to the top? I'm not going to hit you. Why doesn't it fall every time it comes around like that?
Isn't it momentum?
Okay? It has a momentum. You can explain it a lot of ways. Momentum is one of them. It has a momentum that's going at the top, it's going like this, right? And so the first law says that it'll stay going like that unless a force acts on it. And that force, well, normally what makes this come down? Gravity. So that force is going to make it start to fall, but if it's moving sideways, it's going to go in an arc rather than go straight down. And to go in a circle, the downward force at the top has to be equal to the mass of the object times v squared over r. Well, if you're going fast enough, the acceleration v squared over r may be bigger than the acceleration of gravity. And if the centripetal acceleration, the acceleration necessary to go in a circle is bigger than the acceleration of gravity, then gravity isn't enough to keep it in the circle. It would actually go off like this and not stay in the circle just because of gravity. And so you have to have an additional downward force, that's the tension, to get the amount of centripetal acceleration needed. So in this case, at the top, the centripetal acceleration or centripetal force is the result of both gravity and tension. And of course, as we had a question, by swinging around like this, and I let go at the instant that the bob is pointing from my hand toward Maxwell, what direction will the bob go? It's going to go low. Now, Max, you should have the easiest one. Since it's going like this, what's perpendicular to the direction from me to you? Well, other direction.
When you let it go here, it goes to me.
No. If it's pointing straight at you, then it's going to be going perpendicular, so it's going like that.
Yeah, so you let it go here to get it to me.
Yeah, if I want to hit you, I have to let go when it's here.
Yeah.
Because it's going to keep going in the direction it's moving at that instant. All right, next chapter, chapter 7. Chapter 7, we introduced work and energy. You may or may not recall, but you were really, really tired of forces at that point. And then we introduced a whole new way to solve the same stinking problems. We learned to solve those problems using Newton's second law. If you identify a problem is going to involve Newton's second law, you're going to draw a free body diagram, break forces, choose your component directions if there's more than one direction, break forces into components, apply Newton's second law in each component direction. Those are your steps for Newton's second law, solution to a dynamic problem. Work energy gives you a second way to solve dynamics problems. It's based on forces again, but now it's looking at work energy instead of forces. So you had to understand forces before you get to work energy. If you didn't, we would have done work energy first because the work energy is generally the easier way to solve a problem. So if you have a choice, choose work energy because it's usually easier. So with work energy, we first had the first law of thermodynamics. I laugh again, The first law is like conservation of energy. No, it is conservation of energy. So energy can't be created or destroyed. It can only be converted from one type to another. And then we introduced what work is. Work is a force combined with motion parallel to that force. So for instance, we write the equation, non-calculus version, work is equal to force vector dot delta x vector. What does that dot mean?
Cross.
No, this is a cross.
Parallel products, right?
Okay, dot means you're multiplying the parallel parts. If you have a cross, then it's called a cross product, and that means we're multiplying the perpendicular parts. So that means we're multiplying the parallel parts of the force. So if I'm just looking for something I can grab. If I take her phone and I lift it up, am I putting a force on it?
Yes.
Yes. And while I'm lifting up, is it moving?
Yes.
And is that motion parallel to the force in any way?
Yes.
Yep. That means it's doing work. If I go like this, it has a force, it has motion, but the motion is perpendicular to the force. Then no work. So that directionality, having the force parallel to the motion, is important for work. And energy, I define energy as the ability to do work. The ability to apply a force and have something move parallel to that force. And we had two ways we talked about having energy. One was kinetic energy, energy in motion. If something is moving, like think Indiana Jones, the Raiders of the Lost Ark. You have this big ball rolling towards you, a stone that's 2 meters in diameter. If it hits you, can it make you move? Yeah, because it's moving. And so that's kinetic energy. And when we first introduced this, kinetic energy was just 1/2 mv squared. But then we learned that there was also rotational kinetic energy. So we had translational kinetic energy was 1/2 mv squared. Rotational was 1/2. And then we have the rotational equivalent to mass. Comes up in a later chapter, but I'm covering it now because we are putting it all together. What is the rotational equivalent to mass? I asked Randy because he's writing a whole paper about this right now. It's probably what he's doing instead of coming to class.
It says in the calculus test.
Calculus test?
So,
That's not permitted.
No, it's permitted. You can have an exam, as long as it's not the final exam, you can have an exam any day except for dead day.
Oh, yeah, no.
You should know that.
I'm just saying the exam isn't until noon.
Oh, you're in the same class as him?
Yes.
The moment of inertia, is the rotational equivalent. Remember, inertia is another word for mass. Inertia is measured with mass. Moment of inertia or rotational inertia is the rotational equivalent. And for Randy's class, they talk about like the first and second moments and things like that. They use different terminology that actually makes them sound more similar. And then we multiply by the rotational equivalent of velocity squared. What's the rotational equivalent to velocity? You got to just throw one word in front of it. Angular velocity. So remember, we did the problem with the racing of the sphere and the cylinder. And as they roll down without slipping, you're going to have energy distributed between kinetic energy and potential energy, rotational kinetic energy and translational kinetic energy. And as a result, the one that had a higher moment of inertia is going to have more rotational kinetic energy, has hence lower translational kinetic energy, and go slower. Then we had potential energy, the ability to do work because of location or configuration. So for instance, if I lift this up and I let go, it will fall down and mash my hand. It had potential energy here because of its position. When I let go, the force of gravity did work on it, converting that potential energy into kinetic energy. And then when it hit my hand, the kinetic energy is what actually did the work on my hand. So potential energy is based on configuration. We had gravitational potential energy, mgh for the simple form of gravity, or minus g m1 m2 over r for the more complicated form of gravity. Negative. So as something gets closer to the center of the Earth, its gravitational potential energy is decreasing as it's getting bigger in magnitude but more negative. If something drops with the normal one, it's decreasing, staying positive but getting smaller. Elastic, that's what we've just been talking about. Potential energy for a spring is 1/2 kx squared. You might recall doing that last week. Electromagnetic and chemical, we have not talked about those. We're not even going to talk about chemical energy. We reserve that for chemistry class. But we will talk about electromagnetic energy next semester. And then nuclear energy. Yep, we'll talk about that too next semester. Other types of energy, thermal energy. Well, we spent a lot of time talking about that, right? We only had an equation for internal energy of an ideal gas. But that is, once again, energy, things moving around, they have an ability to do work because of that. Unfortunately, the second law says we can't perfectly convert that internal energy into mechanical energy. Vibrational energy, that's vibration something or energy something has because of its oscillation, which is actually a combination of kinetic energy and spring potential energy. Acoustic energy, that's the energy in a sound wave. Seismic energy is the energy in an earthquake wave. Work energy relation. the net work, excellent, work net equals change in kinetic energy. You guys see how the work appeared and disappeared? I don't know why. So net work is change in kinetic energy. That's the work energy relation. And then because we define change in potential energy is equal to minus the work conservative, then the work net is equal to work conservative plus work non-conservative is equal to change in kinetic energy. Substitute here minus change in potential energy plus work non-conservative equals change in kinetic energy. And you get to the form of the work energy relation we usually apply to a problem that says work non-conservative is equal to change in kinetic energy plus change in potential energy. So this is where we get to how to solve work energy problems. Everything down to here in this chapter was just defining what these things are. But to solve a problem with work energy method, you're not dealing with vectors. Remember, forces were vectors. We had to apply Newton's second law in each component direction. With the work energy relation, it's not a vector. So all you have to do is calculate the kinetic energy at the starting and ending points, the potential energy at the starting and ending points, and then any non-conservative work that may be done. What would do non-conservative work? Friction. Friction is our classic force that does a non-conservative work. We could also have somebody pushing on something. That's non-conservative because conservative, you put energy in, it'll give it back. When I push on something, I'm expending energy, and there's no way it's going to, I push a car up a hill, the car's not going to come down the hill and give me my energy back. Right? It's just not coming back. So that's non-conservative. Up at the beginning, we had work and energy definitions, power. Power is something that students often forget about. We introduce it here, and then when we talk about it later, they think about energy and forget what power is. Now, I did mention power in lab yesterday. Power is the rate at which work is done. So power is equal to work per time or change in energy per time, because it's the rate at which energy is converted. Work is a form of energy conversion. Heat, you learned, was also a form of energy conversion. This one here, work done by variable forces. When we say variable forces, we mean a force that's changing, and force times distance moved. If the force is changing, then you can't just take the force times the distance because you have changing forces. So we can find the work done by variable force by taking work is equal to the area under force versus position graph. So sometimes you're just given a graph and you have to find the area under the curve from point A to point B to determine how much work was done during that period. And springs I already covered over there. Okay, I will pick up with chapter 8 next class period. Right now, good Sir David is going to lead you through the teacher evaluation stuff. And so I am going to stop the recording here because you could say sensitive things while I'm